we should probably get started. So today's seminar speaker is Timothy Bretl. So when I got actually put in charge of hosting this seminar series, I happened to be at a NSF meeting, and I wanted to I wanted to capitalize as much as I possibly could. And I happened to be sitting next to Tim, and I was like, Tim, you've got to come and give an RI seminar. He was the first taker of my first experience in hosting these, so hopefully this goes well. If not, you guys can send me angry emails. So Tim, I'm sure will tell you more about who he is and what he does. He's a professor at Urbana, Champaign. He was at Stanford, did some really cool work during his graduate days way back when, with climbing robots. Has sort of done something from everything in robotics, and hopefully we're going to see some of that here today. But without further ado, Timothy Bretl.
Thanks, Matt. Well, it certainly is a pleasure to be here. I mean, it's a great place, obviously. Thank you for the invitation. And I've gotten a chance to talk with a number of you today, and hopefully can connect with the rest of you after the seminar. So I'm going to talk about three very different things today. And I guess all of them are linked by a certain element of surprise. I mean, this is the type of research that I love, where you have a problem that seems hard, and then you learn something, and poof, like the problem just seems to go away. So hopefully I can convey some of that excitement. The other thing that I want to do along the way is, hope this works. There we go. Okay. The other thing that I want to do along the way is tell a little bit of a strange story about my involvement in a prison education program. So I guess so I'll talk about this a little bit as we go, but just to set the stage. Over the past 5 or 10 years, I've been involved in something called the Education Justice Project at the University of Illinois. And I guess one of the flagship activities of the Education Justice Project is to facilitate the teaching of upper division undergraduate courses at this facility. So this is Danville Correctional Center, which is a medium security adult male institution or prison in Danville. It's about a 45-minute drive east of our main campus in Champaign, Urbana. And so this is a facility that has anywhere between 1,500 and 2,000 incarcerated men. And of those, anywhere between 50 and 100 are part of the Education Justice Project. And to become part of this, they would have had to apply. They would have had to have obtained the equivalent, either have a high school degree or get their GED. And they would have had to have taken some amount of lower division undergraduate coursework through a community college that also operates in the facility. And so this has been a remarkable experience. So I guess I've taught 2 courses there, and these are the same courses that I teach on the Urbana-Champaign campus. So I taught one senior level course, just a sort of standard introduction to robotics course there, basic robot kinematics, and I've taught a junior level course in control theory, the same one that I teach to my home department at Illinois is Aerospace, and this is the same one that I teach to juniors in that department. I'm in the minority, so most of the courses that are taught there by faculty and in some cases graduate students from the university are not in engineering. But one of the things that, I guess one of the reasons why I wanted to mention it today is that this is an example of an opportunity for which we are all, I guess, uniquely qualified, right? So this is not me volunteering to tutor or something like this. This is me teaching courses for which the men incarcerated at this facility receive credit from the university, right? And it's not just anybody off the street that can teach these courses. These have to be faculty or graduate students. Go ahead, Howie.
Yeah, so I'm sorry to interrupt.
Yeah.
Again, this is one of the many reasons why you're a better person than I am. So this is great, and I'm so proud and happy about this. So I'm just curious, what kind of support do you get? Do you get TAs? Do How many kids in your class?
So yeah, this is a very good question. And so I guess the short answer is in the robotics course, there were 13, of which 12 finished. And in the other course, the controls course, there were 6, of which 4 finished. I do not get support. This is a challenging environment, and I'm going to say more about this as we go. All right. And I would say that another thing just to add is that this is, of course I do this because it's very clear for a number of reasons that this makes a significant positive impact both on the men and on the communities from which they come. But I also do this because I get something out of it. And it's sort of the same way that I think about teaching in general. I get a lot out of it, right? So this is not me being, a good person or whatever, like volunteerism or anything like this. I wouldn't do this if this wasn't having a significant impact on me as well. Does that make sense?
Thank you. I'm going to follow
Yeah.
with you.
Okay, yeah, and I should just say, so I have a lot, I could talk for hours about all of this stuff. Feel free to interrupt, right? Let me do the time management. I'm happy to skip large portions of what I had intended to talk about, so don't be shy. Okay, let's dive into the first technical. So I will talk about technical things, and here we go. So I guess one set of work that I have really enjoyed doing is on the topic of manipulation planning. So that was something that I think we all would consider to be, classically we would consider to be relatively easy. So 2 robots manipulating a single rigid object, maybe among obstacles. Here's something that we would, I think, all of us generally consider to be quite a bit harder. So this is 2 robots that are manipulating a wire or a cable or some other deformable object. And I guess to me, one of the key reasons why you'd consider the first one easy and the second one much harder is, I guess it has a lot to do with maybe the configuration space in which we're working in these 2 examples. So in particular, in order to describe the placement of a rigid object, I need specify only its pose, right? But to describe the placement of the wire or the cable, I need not only specify its pose, so the pose may be of one end of the wire, but I need to describe its shape. And pose is something for which we have very nice canonical ways of, we have canonical representations for that. So this is position and orientation, right? There's all sorts of different ways of describing those. And I guess the space of poses is something, we understand a lot about the structure of that space. This is a smooth manifold, right? It's a finite dimension. Right? We know a lot about it. And I guess one of the things we know in particular is that given 2 nearby poses, we can interpolate between them. Actually, given any poses, we can interpolate between them. This is a path-connected space, right, if we're ignoring the manipulators, which is really convenient for planning and control and these sorts of things. So the same is definitely, at least at first, seems definitely not true about manipulating a wire or a cable. And the reason is, shape, the shape of that wire or cable is a curve, right? Maybe of its center line. And this is not something that lives in a finite dimensional space. It lives in an infinite dimensional space. And even to describe an element of that space requires some amount of approximation. And it's not at all clear how to interpolate, or whether we can interpolate between nearby shapes. And it's certainly not clear that we can always interpolate between shapes without somehow causing a collision or cause the wire to go unstable or snap or any of these sorts of things, right? So it's for all these reasons that you would think that manipulating a wire or a cable is much harder than manipulating a rigid body. And one of the things that I thought was really surprising and that is really kind of neat is that it is possible to explicitly describe the set of all stable and so quasi-statically stable and collision-free shapes of a wire or a cable. And that just like, just like SE3 or something, just like the space of all poses, this is a smooth manifold. And this happens to be a manifold that, not only does it have finite dimension, this is not an infinite dimensional set, but it's one that admits a parameterization by one chart, a single set of numbers. You don't even have to switch between, different sets of Euler angles or, the equivalent of whatever that is, right? And this is so I guess this is coming out of work I started maybe 6 years ago or something like this. But the thing that's a bit more recent, which I'm still kind of amazed, is that the set of shapes of this elastic object, this wire or cable, that is path connected. in the same way that SE3 is path connected, the space of position and orientations. And I can give you a formula to go from any shape to any other shape, again, ignoring manipulators, that's guaranteed to be stable and collision-free. And that, I think, is kind of wild, right? And again, if you think about this, this makes a problem that classically seems very hard really no problem at all, right? It's not even a planning problem anymore. Right? So I want to give you a flavor of where that result comes from, and whatever. There's a bunch of details we can talk about another time. So the two key concepts are, one, optimality, and two, a certain type of scale invariance. So let's go for it. So I guess optimality is really about the recognition that stable shapes, so I hold a wire in two hands, it achieves some shape, the shape is stable, that's not an arbitrary curve, that's an energy minimizing curve. Right? These are very special shapes that you actually realize in practice. So I think maybe the easiest way to kind of get the point across is to look at a much simpler example. So rather than look at a wire or a cable, maybe think first about a linkage. So here is something with a number of rigid links that are connected by revolute joints, where we imagine that in each joint I have placed a torsional spring. So if I hold this thing by both ends, it will relax into a certain shape, right? And again, that shape is energy minimal. So this is a nice example because given the angle of the first joint, there are, of course, only two inverse kinematic solutions, at least that satisfy certain joint limits. So there's a left-handed solution and a right-handed solution. And I can go ahead and compute the energy that is associated with each of those as a function of the first joint angle. Are you with me? So that's what I'm doing here. So I guess on the left, I am sweeping out that first joint angle, right, for a given set of boundary conditions. And on the right, I am showing you the resulting energy landscape. All right, so for every value of theta 1, I am plotting first the right-handed and now the left-handed resulting total energy in the springs. Does that make sense? And so again, the point to make is that the shapes that are realized in practice by holding the ends of this linkage in particular positions and orientations are not arbitrary, right? They're not continuous in theta 1, right? There are only, in this case, 4 of them, right? There's this one, this one, this one, and this one, right? These are the minima of the energy landscape. Does that make sense? And so what manipulation is, so here in this example, what I'm doing is I am changing now the boundary conditions. So imagine a gripper, right, taking the position and orientation of one end and moving it around. And what you're seeing is the evolving energy landscape, right? Again, energy is a function of that first joint angle. And you can see, minima appear and disappear. And really, the configuration of the shape is being dragged around, right, by this energy landscape. Does that make sense? You kind of getting the picture here, right? So that's what manipulation is. You change the boundary conditions, that shapes the energy landscape, and changes it, drags the shape around by these minima. I don't know if any of you are paying attention, but just an interesting side note here is that so in this particular example, I started and ended with exactly the same boundary condition, right? But ended up in a different shape. And this is again speaking to why this problem sort of seems hard at the outset, because there are again multiple local minima for particular boundary conditions. So using position and orientation of both ends to try to parameterize shape is not in general a good idea. There's definitely not a unique mapping there. Okay. So that's the idea behind optimality. It plays out exactly the same if we look at an actual wire or cable. So in this example, we're again keep things planar just to be simple. All this stuff extends to 3D, right? So rather than a linkage, we now have I don't have a pointer. We now have an actual wire, right? Where I'm describing the shape of that wire with functions. These are functions, you know, Q1, Q2, and Q3, or whatever. Position and orientation as a function of length. Length here I'm representing by t, and that's varying from 0 to 1. All right? That function is in static equilibrium if it locally minimizes some measure of energy again. This is the continuous analog of the torsional springs or whatever, subject to kinematic relationships. So this is relating position and orientation along the length with strain. Right? So that's what the input U is in this scenario, and given boundary conditions. So again, what's going on? Yeah, go ahead, shoot. That's strain. Yeah, but I guess in the way that I've written things down, you should think of it really as an input, right?
So strain is the change. So the torsional strain?
Yep.
Okay, so that's your change of angle.
Yep, exactly. I mean, and this is just, I mean, whatever. This is a unicycle, right? I mean, anyway, we've all seen. I mean, I have written down an optimal control problem. Right? It's what I have written down. Right, that captures what it means for a shape of the wire to be energy minimal. All right, again, assuming like linear elasticity and sort of the usual assumptions that one makes about the mechanics of an object like this. All right, go ahead. Gravity? No gravity, and this is a very interesting thing to come back to. So there's, I have a strong suspicion that all of the results that I'm talking about extend to gravity. The proofs are a little tricky. Yeah, so I'd love to talk about that afterward. Yeah, it's a very good question. So no gravity at this point. Go ahead.
Unicycles should have to do inputs, right?
Yeah, so how about, what, should I be saying Dubin's car, right? Yeah, okay. Yeah, we're on the same page. Yeah, right, yeah, okay. Yeah, so again, what's happening is, what is manipulation? Manipulation is changing the boundary conditions. Changing the boundary conditions changes the set of local optima of this problem, right? It changes like what the energy minima are. And your shape is being dragged around in exactly the same way as in the example that I showed with the linkage. Does that make sense? So the thing is, like, and again, this is sort of one of the things you see when you write this down in the framework of optimal control is that we all have tools for describing or characterizing the set of local optima of an optimal control problem, right? So namely, we have this thing called the maximum principle, right? And what the maximum principle tells us are necessary conditions for optimality. So again, like the game that one plays is you introduce a co-state, and what the maximum principle gives you is a set of ODEs that, if you choose the initial state and the initial co-state, poof, you have a shape. Right? Again, optimal control, it's a trajectory. Here, we're interpreting that as a shape. Does that make sense? So that is to say that in this example, because, I mean, again, if we assume that the position and orientation of one end of the wire is fixed, everything boils down to the choice of these three numbers, right? The three components of the initial co-state in this example. So that is to say that the space of shapes, the space of stable shapes, is for sure of dimension no more than 3. Right? It is not an infinite dimensional space. This three-dimensional it's a subspace of this infinite dimensional space of curves, right? But the ones that are energy minimal are very, very special, and we can characterize them again, like using sort of standard tools from optimal control. And I guess another thing to say is that the co-state in this context has a direct interpretation, which should have been obvious to me to begin with, but it wasn't. It has a direct interpretation as force and torque. So all I'm trying to tell you here is that the right set of coordinates to describe the shape of a wire or a cable, either in 2D or in 3D, is the force and torque at one end of the wire or cable. Does that make sense? Different force and torque, different shape. All right. So you can go and rigorously prove all this stuff, blah, blah, blah. But the bottom line is that the set of all stable and collision-free shapes of a wire or a cable is a smooth manifold of, in this case, in 2D, it's dimension 3. And it can be parameterized by one chart where the coordinates of that chart are force and torque. Go ahead.
So you're saying you specify forces and torques at both the end, you have a unique mapping to a shape.
So let's be real clear, right? So what actually happens in practice is that like a gripper holds both ends. So what actually happens in practice is that you're enforcing some set of kinematic boundary conditions, right? But the way that you represent the shape is by specifying, or one way, one very nice way, is by specifying the force and torque at one end. So I'm not saying, I mean, like of course this is then realized by the grippers, but again, like what you're doing, you're not doing force torque control or something at one end, right? You are enforcing kinematic constraint. But the result is, of course, also to apply a force and torque at one end, and that's the representation of shape that you're looking for.
But how easy it is to, for example, if you want to do planning in this space,
Oh, it's like super easy.
but you have to do some sort of collision checking.
Yeah.
For that, how easy it is to get the shape once you have the.
Oh, you just integrate those ODEs that I showed you. Right? Yeah, integrate 6 ODEs and poof, you have a shape. But it gets better. All right. All right. So, and this result just kills me. Right. So it turns out you don't have to plan. Right. And this is due to a certain type of scale and variance. And the idea here is that there is a type of scaling that you can apply to the shape of this wire, these wires or cables, that causes them to remain stable and collision free. So let me try to give you a sense of how this works. So imagine I have a shape right in the top left. So imagine what I do is I grab it halfway along, for example, right? And then I cut it. So for sure, if the original one was stable and collision free, right? I cut it and grab it where I cut. That thing for sure is also stable and collision free, right? And then let's say I take that and I scale it by 2. Again, intuitively, and you can very easily show this, intuitively you get another stable and collision-free shape that is exactly as long as the original, but a different shape. Are you with me? So this is a way of constructing new shapes from old shapes. Does that make sense?
Could you do that again? So you
Yeah.
get the original shape, cut in half.
Yep.
Now you have the half.
And then you blow it up by 2.
Take the half. So you grew an arm and blew it up by 2.
Yeah.
Okay.
Yep.
And the resulting shape, the larger shape, is stable.
Yep.
Collision free.
Yep.
Is there some constant, like the energy is double or something?
Yeah, I'm glad you asked. Yeah, so you can go ahead and quantify all this stuff, right? So what's really going on is you've got a solution to those ODEs, those 6 ODEs, right? That the maximum principle gives you, and then you apply scaling. And this is so this look. So first of all, this was a very talented student who derived this result. I'll show you his picture in a little bit. But this, I never thought that dimensional analysis would ever be useful, right? It is useful, right? Because like effectively, what I don't even know why he started playing around. I think it was in the process of trying to non-dimensionalize the model. He started playing around with this, and so essentially he just scaled the arc length by some constant and asked, okay, like what would the exponents have to be in order to make the solution work out? And it turns out they're very simple, and so you can construct new solutions to these set of 6 ODEs from old solutions. That's the bottom line, right? And yeah, so certain things are scaled by L inverse, other things are scaled by L squared, like whatever, right? I don't remember exactly how the energy scales, but we can talk about that afterward. Anyway, so the point is there's a quantitative way of going from old solutions to new solutions, right? And what's happening is, again, you take a thing, you cut it somewhere, you blow it up till it was the same length as before. And for sure, if you started with a stable and collision-free shape, you end up with one. But the beauty is that if you scale enough, you can also take a shape that was not collision-free and make one that is collision-free. Do you get me? All you have to do is cut far enough back so that you get rid of the collision, right? And it turns out that exactly the same thing is true about stability. It's a little bit harder. I haven't figured out a good way of visualizing stability. But suffice it to say, this is an example of an unstable shape. So this would kind of snap through, if you like. But if you scale this back far enough, right? So cut far enough back and then grow, right? You end up with a shape that is stable. Does that make sense? So this is, yeah, go ahead, Howie, yeah.
This would be a stupid question, but
Yeah.
if you're always going to be anchoring both, what does an unstable shape look like then?
Well, this is an unstable shape. This is not realizable, right? It's going to like snap through or something. Yeah, for fixed boundary conditions.
So
Yeah.
if you start with that unstable shape, cut it early enough,
Yep.
you can make it a stable shape.
Yep. So this is awesome, right? So it allows you to do things like this. So this is effectively both the proof of path connectedness and an analytical way of constructing like feasible paths from unfeasible ones. So I guess at the, well here, so remember, configuration space for shape is 3-dimensional, right? 2 forces and a torque. I am visualizing that space here. Here is a path through that space from one shape to another shape. What those points represent, so like the green one, is this shape, okay? Stable and collision free. So here I am following that path. We get collisions and we get instability at certain times, like whatever, right? So this is a path in the space of shapes that is not feasible. Does that make sense? So what one can do, given this scale invariance property, is I guess maybe look at the top right would be easiest. You take that original path in configuration space and you scale the whole thing down. So every point along the path, you scale that down to where it is stable and collision free. Does that make sense? And yeah, go ahead.
By looking at the
Yep.
path in the configuration space, can you, how do you say if it has self-collisions or not?
Oh, you have to test, right? Yeah. But there's, I mean, just I don't know, FYI, there's a result. So to show that this is always possible, you can show that there's a ball around the origin so that there is, so it is always possible to scale sufficiently far to make the thing stable and collision free, I guess is the way to say that, right?
In this case, you're like iteratively testing which part to scale and by what factor to scale, and then finding which one works.
Yeah, I mean, I'm scaling all of them by the same amount is typically how you would do it. Yeah, yeah. And so they're smarter and, yeah, go ahead.
So you said earlier that given the same initial conditions, multiple local minimum, multiple local minimum.
Yep.
So if you want to construct a particular shape, this would seem to be an ambiguous approach.
Nope. Just remember that, so these points, there's a one-to-one mapping from this to shape, right? However, there's a one to, or I guess, how about a many-to-one mapping from these points to boundary conditions? Does that make sense? So every point in here uniquely specifies a shape, but many different shapes may have the same boundary conditions. So what one actually does is you start in some shape, that's a point in here, right? And then you plan, again, this is like very, like this is how we do everything, right? We plan in configuration space, and then you realize the path in configuration space by motion of the grippers. Does that make sense?
So how easy is it to go from the point in that configuration space to the boundary?
It's as easy as integrating a set of 6 ODEs, right? So very easy, right? Compared to, again, like the way that people were trying to do planning like before, right? Which is essentially to, whatever, like do sampling-based planning in the space of boundary conditions, right? Yeah. So anyway, whatever. You take the whole path, you scale it down, and connect the ends of the scaled down path to the ends of the original path along the scaling curves, which again, along those scaling curves, you're again guaranteed to be stable and collision free. So the resulting path is this one, right? Which again is always stable and collision free. I think maybe maybe a more intuitive way of visualizing this is like this. So on the left, you will see the original path, the original motion that will have instability and collision. On the right, you will see the scaled motion that won't, right? I guess what I'm indicating here, like this is the cut on the left that produces the scaled motion on the right, which again is realized by moving the robot grippers, right? Which locally, motion of the grippers and motion of the shape, these correspond one-to-one. It's just globally that you have these problems, right? Isn't that neat? Anyway, I think it's really neat. Right? So the result is, so you can prove that this is always possible. Again, this is a constructive proof using the method that I just described. And the result is that not only is this space of shapes really nice, well-behaved, all these things, it's path connected, right? Which I think is kind of neat. So the student who proved the path connectedness result in particular, his name is Andy Borum. He's now at Cornell. He's a visiting assistant professor there in the math department. He's an absolutely wonderful guy, right? I'd be happy to put you in touch. So I guess, so another thing that Andy did was help me teach at the prison. He actually became very involved over there, right? In particular, the very first course that I taught over there was this course in robot kinematics. This is a full semester course. They got the same credit, same course, same topics that we do on campus. There were certain things that very definitely had to change. So one does not bring robots into a prison, right? Although and this kind of speaks to the challenge of the situation, is that they don't have a rule that says no robots in the prison, right? They have a rule that says no cell phones, right, for obvious reasons. They don't allow internet in the prison, right? They have certain rules, very definite rules about clothing, right? But they don't have a rule that says no robots or things like that. And so what tends to happen is you get a lot of self-censorship for people like me who are going in. Because if I were even to, for example, ask if I could bring a robot in, right, or bring like whatever, like the linkage that I showed or anything, right, that might cause there to be additional scrutiny, both of what I was trying to do and what my colleagues were trying to do, that it could be very bad, like programmatically, right? And so this sort of thing, you can sort of, again, like it's a little bit difficult to convey this feeling, but it's a definite fear that we all had of the guards and sort of the structure, right, the institution in the same way that the men, of course, have, right? So there were very definite changes that had to be made. So labs were not, they didn't go and program robots. I chose to focus that on analysis. We can argue about whether or not that was, an adequate substitute. I think that we preserved to a large extent the intellectual content of the course. And certainly we got through, at least as much as we would have gone through on campus. And there were very, very significant differences as well in the background of the students. So maybe to give you a little bit of a sense there, the students that I was interacting with, these men had typically been in prison for at least 10 or 15 years. Many of them were incarcerated as teenagers. One I know as early as 13 years old, right? So you can decide for yourself the extent to which that's just. These were, the crimes, you don't tend to look that up, right? But these were serious crimes, whatever they were. A lot of these men came out of, Chicago sort of South Side gang violence back in the day, right? So, bad things happened. So many of them have been in for a long time. And so one big difference is that these are very mature students. And their motivations are very different in general. You don't want to homogenize the group, but they're very different in general from the motivations of undergraduate students on the outside, in the sense that an undergraduate student on the outside stereotypically is going to get a job, right, after graduation. That's a big motivation, right? These students that I interacted with, they're just not going to get a job. Many of them are going to be released, but none of them are going to be roboticists necessarily, right? Again, who knows, right? But that's they face many challenges when they're released. So their motivation, they describe it as wanting to become educated men, right? It's sort of a very liberal artsy type feel. You do not want to romanticize this situation. But there was a certain depth to that, right? That isn't common on the outside. So there were some sort of interesting pros and cons, I guess, right?
Out of curiosity.
Yeah, go ahead.
What was your I'm sorry. What was your interaction with them other than did you have any interaction with them outside of the lecture?
This is a very good question. I'll say more about this in a second, but I guess the direct answer to that is that I taught for 3 hours on Friday nights. And outside of that, my interaction was, so I did occasionally go in for office hours, which would be another 3-hour block, but it's just not sustainable, right? This isn't my job. I'm not going to do that every week. So I would do that, 2-3 times in the course of the semester. And then there's sort of very sporadic written correspondence could happen, but largely it was entirely that Friday evening, right, which is another big challenge.
So I find it hard to believe that these gentlemen were able to build up the background to even have multiplying interests.
Yeah, we had some challenges. I think one way to put it is that, so again, thinking about differences. The prison environment is not ideal, but they in general have a lot of time, right? So when you tell them, like, okay, here's a hole in your background, here's a book that plugs the hole, they'll go read it, right? Which again, stereotypically is very different, right, from how things work on the outside. We all know this, right? So this is not to say they didn't struggle. And this is one of the big things that I had to deal with, right, in the class, and that like really threw me off in the first couple months. I mean, things like derivatives, for example, right? Yeah, so I explained derivatives, right? And it's not that these weren't hard, right? But these are challenges that could be overcome. And this is again one of the things that I took away were these real significant challenges to my own teaching. Go ahead. Yeah. I'm really glad you asked, and this is another big challenge. So in general, they cannot reliably work with other students. Some of them are lucky enough to be cell roommates or whatever with other students, and they may be particularly lucky to be with another person who's in their same class. That's rare. They sometimes share meal times. But otherwise, no. I mean, it's largely individual, except when they can sign up to use a computer lab that we installed in the facility. They can sign up to use what they call a resource room, or kind of like TA-ish type hours. That's where they can interact. But this is another area of significant challenge, is even working with each other. Yeah.
I think most of us in this room are not necessarily old enough to remember what classes were like before the internet. So
Yeah.
explain how in the world you're supposed to, I don't know, I can't imagine doing assignments about the internet or anything like that.
Yeah, so there is a library, right, and there are books, and one can actually look things up, believe it or not. Yeah, but no, I mean you're right. It's a big challenge. There are other programs like this around the country. There's actually, I don't know, there's a famous one at San Quentin, for example, where they do now have access to internet, and this is starting to become more common. There's another program. So Andy actually joined a program similar to ours at Cornell. I don't know exactly what the rules are there. So there are this is anyway, programs like this are spreading, but yeah, I mean, like this is another big problem, is a lack of access to internet as well as other resources. Yeah.
And what about
Yep.
handing out assignments? Did you have a dictato machine?
So I guess I brought copies in. Yeah. No ditto machine. But yeah, and rules change. So the first time I taught a course, I brought in a USB key every time and showed videos and stuff. And the second time I taught a course, that was not allowed. And it was just, that was the way it was. All right, so you kind of roll with it, right? Yeah. All right, cool. Okay, ready for some more? Yeah, so I'm going to talk about more technical stuff. Okay, all right. Okay, so a completely different topic, all right? So several of my students have, I guess, I don't know, I got into kind of neuroscience-y related stuff, and several of my students led us in the direction of prosthetics. And in particular, one student at the Electar worked on prosthetic hands. And so the work that I'm going to talk about now is motivated by prosthetic hands. Right, and in particular, there's a challenge. So even people who have access to prosthetic hands, which large parts of the world don't, even people that do have access tend not to use them, actually. There's a very large rate of abandonment. And one of the reasons is the lack of sensory feedback, right? So not only do you lose the ability to like move your hand, right, but you lose the ability to feel. And so one of the things that Adil was looking at was how do you restore a sense of touch, for example. Anyway, so he built a hand. He's a really interesting guy, very mission-driven. I've learned a lot from him. We could talk about details of the hand that he built another time. I want to focus on the touch feedback part. So there are a lot of different ways of doing sensory substitution. The way that he focused on was a particular one called electrotactile feedback. There are several reasons for this. It's sort of like the reverse of EMG. So EMG, you put electrodes on the skin and you record a differential voltage or something, and that tells you about muscle activity. So here you put electrodes on the skin and you put in a current pulse, for example, like a monophasic square wave, and that produces sensation. It could feel like a tingling or a pressure or a pulse or whatever, right? And so you can vary the intensity by varying the characteristics of the square wave so more intensity means more force, for example, right? So this is what he did, and so I guess the challenge with using electrotactile stimulation is that if you think about, so everything boils down to the interface between the electrodes and the skin. And that interface is affected by all sorts of things. So sweat, peeling electrodes, pressure, all of these things change the effective contact area, which changes, I probably should be saying impedance here, but you get the idea, right? It changes the resistance between the electrode and the skin. And as that changes, the sensation intensity also changes very significantly, right? So here's an example where over time, we had a brave subject peel the electrode off, one of the electrodes off, a little bit, then a little bit more, and then a little bit more, right? And by the time we got to a little bit more, this was causing significant discomfort, right? And the reason for that is because the resistance between the electrode and the skin was changing significantly. Does that make sense? Okay. So there's a yeah. Yeah, we do have IRB approval. Yeah, it's all good. Oh yeah, not at the prison. Yeah. Thank you for clarifying that. Yeah. So okay, there's an obvious solution to this problem if you could do it, and that is to measure the resistance, which you can do because you know the current you're putting in. You can measure the differential voltage so you can get a sense of resistance, right? So if you measure the resistance, in theory, you could modulate the pulse. So change either like the width or the current amplitude to keep the sensation intensity constant. You with me? The problem is that in order to do that, you need a good model of the relationship between these quantities. So the quantities you can choose, the peak of the pulse, the pulse width, and the sensation intensity. Does that make sense? So there's been a lot of work over the past, really like 30 years or more, right, trying to do that. And what we drew from that work were certain key quantities that seemed to be important. So one of them, the resistance is kind of obviously important here. Another is something that's commonly referred to as peak pulse energy. And so, you can think of these as kind of like various integrals over the pulse, I guess, if you like. So this, I guess, just to point out, this is a quantity that can be computed in terms of the things that you choose, which are I and T. And the thing that you can measure, which is the peak resistance, right? And there's various people that have hypothesized various relationships between this particular quantity and sensation intensity, which turned out to be. These were. So this work was critical in forming our own hypothesis, but I guess these prior hypotheses were wrong in various ways, right? And a third quantity is something that's referred to as phase charge, which is just the product of the I and the T that we choose. And again, there are hypotheses for this quantity being related to sensation intensity that were just a little wrong, right? There's also been, I mean, just to give an example of something else, like other folks have tried to relate the pulse duration alone to a measure of sensation intensity. But I guess if you like, the fit was not very good if you were measuring that by R² values. So the thing that, I mean, again, the student at Deal really lucked out on this one. The thing that I found very surprising is that these two quantities, peak pulse energy and phase charge, both vary linearly with peak resistance at constant sensation. So, I guess the experimental protocol is a method of adjustments, which we could talk about offline, no problem. But just to give you the results, what you're seeing here are essentially, so these are lines of constant sensation on plots of phase charge and of peak pulse energy as it varies with peak resistance. Does that make sense? Go ahead.
That sensation is as reported by the user, right?
Yeah, so I guess the way that this generally works is you've got like a reference intensity, and then you have them match the reference by moving things up and down or whatever, and then these are the result of that. So this is done with like a zillion subjects over multiple days, and different magnitudes of sensation, different electrode sizes, like the whole 9 yards, right? And the fit is very, very good, again, as measured by R² values. Go ahead.
So in the graph on the right-hand side of the previous slide, that intersection point seems to be an invariant. What is that?
I have no idea, and this is a good example of an open question. Yeah, and I know there's folks in here who are bio people, right, physiological people, and I would love to have an explanation of that. Yeah, so this, I mean, whatever. So this went into science robotics eventually. If we'd been able to answer questions like this, right, who knows where it might have ended up, right? Yeah, I don't have a good explanation for that. Yeah, that's a very good question. But in any case, this is a very good model. So immediately you can take this model and do what we thought you ought to be able to do, right? Which is you apply the pulse. This produces a sensation. If you want to keep that sensation constant, what you do is you measure this, or you compute the slopes, so to speak, of these lines that you are currently on. And then you go and compute the pulse amplitude and pulse duration given the peak resistance that is being measured. Right, so that's the closed loop nature of this. You compute those two quantities that match the reference. Does that make sense? And the short story is that this works great, right? And maybe I'll skip the data and just go to the demo, right? So this is a person who obviously with a hand amputation, and what he is going to do. So first, what you're seeing here. Actually, let me pause this for just a second. So this is without that method that I just described. And he's going to be peeling the electrodes. So this is the thing that produces discomfort, right? And what I want you to focus on is down here. So this is the slope of the phase charge line, right? And if that slope remains constant, we get constant sensation. If it changes, we don't, right? So without any closed loop, we of course get significant changes in that slope, right? And this is something that the subject causes discomfort for the subject. With the closed loop, we do not get those significant changes, or at least they are damped out quickly enough that you do not get discomfort. Again, so focus on the bottom right. Does that make sense? And again, you do like a zillion runs of this, and you can quantify it, and it works great. So again, focus on this plot, right? Constant, not constant. And I'll just let this go. So this, whatever, you can do elliptical trainer, right, with this running. You can do stairs. Anyway, all the activities that one would normally want to do. This is a very simple, very effective way of holding the sensation constant so that it can, in principle, be used effectively as a mechanism for sensory substitution with a prosthetic hand. You with me on that?
So where does your reference come from?
Aha. This is another very good question, right? So this is an open problem, right? Is the initial calibration a good method for the initial calibration of the reference? So, again, like what you could do is you could have people, so you could do a calibration kind of by hand ahead of time and vary the level of sensation, ask them what sensation they feel, and get the reference from that. That's not what you would want to do in practice. You'd want to have this be done in an automated way, and this changes from day to day. So for this whole thing to actually be implementable, right, you need to somehow address this problem, and maybe there's someone in here who knows how to do that.
But
Yeah.
even one step even higher than
Mhm.
that, how do you decide what sensation to apply? The mapping
Oh.
from?
So this is a good question what the mapping should be. I mean, we just did a linear mapping from, so we, put,
No, I mean,
yeah.
like them holding something or.
Yeah, totally with you. So we had a pressure sensor in the fingertip, and we mapped the measurement that came out of that linearly to the level of sensation, right, in some range. Yeah. All right, cool. So would you like me to be done at 25 after?
I mean, people are asking questions in freeform, so normally we'd probably stop around then and then
Yeah.
questions, but I leave it up to you.
No, that's fine. So I will completely skip the third part of my talk.
What was surprising to me?
What's that?
What was surprising to me?
Oh, yeah. Wait, what? In this part?
No, the
IT
third
reality.
surprise.
The third surprise. Yeah, I'll show you. Yeah, so I'll give you that. Just to face the name. So Adil Akhtar and Kyung-Yoon Choi were the two students behind this, and they're great. Adil is now, he built his own startup to do this kind of thing commercially, of which I have no financial interest, just FYI. All right. Cool. Let me skip this this is just an image of one of the resource rooms, the libraries at the prison. All right. So I guess just the 60-second summary of this. So the third thing that I would love to talk about offline is a way of improving the performance of structure from motion algorithms using fiducial markers. The context for this is very large-scale construction projects. So we're talking like $500 million to $1 billion construction projects, where it's very important to have very accurate 3D models of the sites that are evolving on a daily basis so that you could do things like decide what is ahead and behind schedule, right? Because, like even just a fraction of a % efficiency gain is like, at that scale, it's like $50 million, right? There's significant delays and cost overruns and all these things that happen. You with me? Anyway, whatever. So structure from motion is like SLAM, right? It just takes unordered images instead of ordered images. So one of the things that, this algorithm tends to break a lot. And when it does, this is very bad because it's much slower than SLAM. It is not a real-time algorithm. It takes hours and hours and hours and hours to run. And this is very bad, again, in the context of the construction application that I talked about. So one of the things that you would like to do, if you could, is play tricks like introduce fiducial markers that, in principle, would allow you to make the thing work better. So everybody has seen markers like these. These are great. They provide a stable source of features. So the thing that I found very surprising is that there are very ineffective and very effective ways of using them, right? So the ineffective ways, which I think are obvious and are things that you would try first for sure. So one thing you would immediately try, and I've done this, is to just treat these markers as additional texture. That's a horrible idea. because what you're doing is you're introducing texture that all looks the same. Right? This is more repetitive features. The second thing that you might try to do is add like the marker corners as additional tracks, if you like, so additional matched features in your structure for motion algorithm. That provides some benefit, but the benefit is marginal at best. A third thing that you could try to do is use only marker corners rather than all the other features that you would find in an image. So that tends to break. And it tends to rely on there being many markers in the scene, right? So that does not degrade well with few markers. So these are examples of obvious but totally ineffective ways of using markers. And the thing that was surprising to me is that there are very simple ways to use markers that are not obvious, at least they weren't to me, that are much more effective. And effectively, the way to think about this is that you use markers to do two things. One of them is to filter the candidate images that you try to match. So essentially what we do is, if two images do not share a marker, you assume that they do not overlap. You don't even try to see if they overlap. This is extremely effective. And the second thing that you do is, I don't know if anybody that knows anything about SFM, right? You know that, again, these are unordered images, and eventually you have to start building up a 3D reconstruction, and you do that by adding images incrementally one by one. And the order in which you add them really matters. And there are all sorts of tricks for doing that, which are not very robust. Using markers to order that process is very, very effective. So essentially what you do is you count the number of shared markers between an image that you want to add and an existing reconstruction, and you order by whichever shares the most, with matching features breaking ties. And again, these are not the things that we thought of first, but these work really, really, really well. Again, we can talk about methods, we can talk about results later, but the method that I just described outperforms everything else that you could think of, right? Including those obvious but ineffective ways of doing things, right? And this is also a demonstration that if you didn't do what we're suggesting, it's often better to mask the markers, to completely ignore them, right, than use them as texture. Which again, in answer to your question, Howie, is something that I found surprising. Anyway, I really don't want to go over time. This work was done by Joe DeGaulle, who's now at Microsoft Research. It was also done jointly with Derek Hoym, who some of you probably remember. He's a great colleague at Illinois, and I encourage you to get in touch with Joe. It was pretty neat work. I think rather than say anything more in a formal setting about this, happy to answer more questions. I can't say enough about how much I've gotten out of my involvement with this work in the prison. It really has contributed to my own growth as a teacher and maybe a little bit as a person or whatever. It's put me in touch with not just the incarcerated men, but a really interesting group of colleagues. And I guess just to maybe leave you with a fun fact to demonstrate one type of impact that this has. So I think we all know that, so I have 3 kids, and the fact that I have the fact that I have degrees, right, that I've had higher education means that they are much more likely to go to college, right? You don't have to, kids, but yeah, they're much more likely to go to college given that I have a lot of education. So it turns out, and there's data to back this up, that so these incarcerated men, many of them have children as well. They don't even have to get a degree. If they take any courses in prison, their children are statistically more likely to go to college. That's nuts, right? So this thing that we're doing in prison with men, some of whom will never be released, has a positive impact on their communities back home, and and that's all of us too, right? So anyway, yeah. So go Google it. There's a nice video, and I'll stop there.
Thank the speaker. We can open it up for any unanswered questions, or does anybody have anything? Yeah?
Go ahead.
You changed your teaching on campus to always come.
Yeah, so this is a really good question. So this is a question I haven't thought very carefully about. It deserves some reflection. I think that, so I think one of the things, so I am not going to answer that question, right? But let me give you an example of something that it did force me to do, and I think some of Howie's questions have pointed to this. You very much have to think on your feet in that setting, right? Not only in terms of, what are you prepared to talk about or what resources are you prepared to have available, right? But also, to respond in a way that's patient and open with questions, right? And try to meet students where they are. Nothing is profound about what I just said, but as we all know, this is something that takes practice, and this is an environment where I had to practice that a lot. Does that make sense? So I think your question is a very good one, and I'm going to have to reflect a little bit on some of the more specific ways that it's changed what I do, but it certainly has helped, and that's an example of how.
What do your kids think of this?
I don't know. What should they? Yeah.
I don't know, I'm a kid.
So I think they grew up with it. So they're 11, 8, and 3 now. And so I did this first in 2013. And so I guess my oldest was 5 at the time. So it's not like, it's just a thing that one does. And I'm actually kind of happy that they would think of it as normal. So this is a good question. Maybe I'll ask them. I'll ask them tomorrow what they think of it. Yeah, I think that's a good question. Yeah, they don't. I assume they don't hate me because of it. They haven't. Yeah, shown me the. Yeah.
Maybe you'll ask to know.
Go ahead.
I know you
Yeah.
said that all your students have very different, they had different motivations for wanting to take the classes.
Yeah.
In general, just to become educated, which is pretty broad. Can you give any specific examples of something more concrete or how they might use just learning kinematics to buy some choice the next class that they might take, or reading the books that they might request to read, or anything?
Yep. So I'll give maybe 3 examples, and there's like as many as there are people. So one is there's several students. This has happened to several students. One in particular was released and then went to a 4-year degree program, right? And they were admitted in part because of the courses they took inside, right? A second one, I don't know what his situation is now, but he had this idea so he was released, somewhere between these 2 courses that I taught. I sat in on his. We do like exit interviews or whatever in the program, and his dream was to start a shoe company, right? I don't know how that flowed from our course or anything, and I don't know whether he was successful. He faces a lot of challenges, but that was something that he wanted to do, right, as a result of this. What was my third example? Just to give another example of like what happens here. So I guess one of the very important parts of this is that the men who are involved start to take some agency in their own situation, which is again largely controlled. So one neat example, this is a totally different part of the program. There's a very active English as a second language teacher training program as part of the Education Justice Project. And so the men who are part of that, they're learning to teach ESL teachers or whatever. And the people they teach are other incarcerated men in the facility, right? So it's kind of like spreads that way even before they're outside. So these are just examples, right? And I'm sure there are many others. Does that kind of answer your?
No, I just wanted examples.
Okay, yeah.
Along the same lines of that, given that they're very limited in what they can do, has any of them expressed interest in research, that they're probably going to be there for long?
Yep. So this is, I guess there's, the short answer is yes. And they have published papers, in fact, right? So I don't believe anyone has done this in the area of math or science or engineering. But they do publish work. Well, anyway, so I'm not going to be able to cite them now, but I'm happy to refer you to them offline, right? So these are in non-engineering fields across a range of topics, and some of the work is quite good, right? There's a lot of stuff that you have to negotiate here. I mean, particularly if it's like co-authored with folks on the outside. So anyway, but yeah, we don't need to wade into the details. But yeah, the short answer is yes. This is, for some of them, this is a goal, and they do it, right? Other things that are popular are like creative writing is sort of one of the other things you might have heard that many people on the inside do. So yes is the short answer. Yep.
So if you just imagine taking like a 13-year-old off the street and putting him in this environment where he's rarely allowed to socialize with anybody, and probably before he went in, had a lot of bad influence in his life. So do you see? I mean, it seems like they're kind of frozen in a situation that it's not great for socialization in general. So has that been a challenge at all, teaching people in that environment?
Okay, so with so I guess ignoring the last sentence, it is a miracle, right? In some respects, that they are where they are, right? And it speaks to their own growth because it's not easy, right? For exactly the reason that you just expressed. I never saw any of that because again, my interactions were very good. This is a very select group of men. And they did have to apply and like all this stuff, right? So largely, they're the ones protecting us from the environment, like rather than any other way around. I think the other thing to point out is that, I guess where you started with this is that, yeah, it's completely inhumane to take a 13-year-old and put them in this environment, and a large. A not insignificant fraction of the more than 2 million people in this country that are in prison are like from that type of situation, right? So in part, my involvement stemmed from, this is sort of a very small part of a much bigger effort. But yeah, this is just not acceptable, right? Something about the whole system needs to change, and I think we've all seen that. There's whether this is through what you hear about in politics or read the new Jim Crow or like whatever, right? It's kind of in the air that something needs to change about this system, and again, it's for this exact reason, right? Yeah, so I like the way that you put that.
Cool. All right, well, let's thank the speaker again.
Yeah, sure.